Welcome to the lectures on modern digital communication techniques. So, we have discussed about inter-symbol interference, and we wanted to transmit at the maximum rate of signaling without having ISI or 0 ISI. But the constraint that we found is realizability of the filter, because of which we required excess bandwidth. So, since that causes some wastage of bandwidth, we wanted to investigate some methods by which we could restrict ourselves within the Nyquist bandwidth and yet have communications at the Nyquist rate, that is 2W symbols per second, for which we introduced the kind of signaling techniques known as partial response signal, and we are introducing the pulse shapes or the signaling scheme known as duobinary signals. So, we explained briefly how the pulse shape would be. So, the pulse shape that we have is the solid over here, which has non-zero values at 2 sampling instants. So, in this situation there will be another pulse which would begin here and it will continue in a similar fashion. So, it will cause inter-symbol interference, but since it is controlled, we should be able to handle this inter-symbol interference. The other pulse shape is mentioned here, which also allows some kind of ISI in a similar manner. The XNT, that is when described at sampling instants, is mentioned as if it is 1 at n equals to 0 and 1, and it is 0 otherwise, that means in other situations. So, if you take the Fourier transform for this, the spectrum would appear as described over here for frequency less than W and 0 otherwise, and this can also be viewed, if you expand this, you could view it in terms of e to the power of j 2 pi by W f. That means, if I take e to the power of j 2 pi W f out, you are going to left with a e to the power of j 2 pi W 2 pi f by 2 W plus e to the power of minus j 2 pi f by 2 W, which works out to be 2 cos of pi f by 2 W, which we have over here, and 2 and 2 cancels out. This is the common factor. So, which has an expression which looks like this. There is a phase term and there is a cosine kind of roll off instead of rectangular roll off. So, if we look at the spectrum, we will find the spectrum takes a form from these expressions above as given here. So, for the duobinary of the solid black impulse that we shown on the left, you have the spectrum which is cosine as you are seeing over here, and there is a phase which is e to the power of j 2 pi f by 2 W, and for the other one you have the spectrum which looks like this. So, if we focus on this spectrum, it is much more realizable, it falls off smoothly, and beyond that it is 0. So, this is much more realizable than the Nyquist filter, and we would restrict ourselves within the W spectrum that we need, and yet we are able to signal at Nyquist rate. So, the other case, which is the red one, is indicated by the corresponding expressions of x t in the red color over here, which has 2 sync, the plus and a minus, as you can see, plus and a minus. There is an offset of plus t and minus t. So, you have this offsets, right, and it can be described as 1 for n equals to minus 1, that means, at that sampling instant it is 1 at n equals to minus 1, and it is minus 1 if you look at this value, it is minus 1 at n equals to 1, at n equals to 0 1 and 0 otherwise, it is 0 over here, 0 over here, and 0 at all the places. And in terms of frequency response, it is e to the power of j something minus e to the power of minus j, and this is 2 j sine pi f by W. So, 2 and 2 cancels out, you have j by W sine pi f by W for f restricted within this and 0 elsewhere. So, these corresponds to the next set of pulse shapes that we are looking at, called the duobinary signals. So, if we look at what happens I mean, before we proceed further, just let us quickly take a look at the general class of band limited signals with partial response can be expressed in this form. So, if you compare it whatever we have there, there is a sink plus a sink, here there is a sink minus a sink. So, you have a summation of sinks and you have values of x n upon 2 w, which can be plus or minus, and in the frequency you have again a form e to the power of j pi f, and x can take different values, according to which you are going to get spectrums which look like this. So, this is a general form, and Krejcima and Luckey, they produced other interesting pulse shapes, but they are pretty complex. So, we would restrict ourselves to the study of duobinary signals as discussed in the previous picture. So, if we now focus on the data detection, so there are several ways of detecting the data. Ideally speaking, since we have memory in the system, so we should use some kind of a memory based demodulation technique. So, that means there is a sequence that we should concentrate on, and because of the sequence we can use the maximum likelihood sequence detector, because there is memory involved, there is a sequence, not symbol by symbol. However, that is very complicated. So, we will focus on a symbol by symbol detection, although it is suboptimal, but still it serves of great purpose, and it also gives us insight into realizability of such systems. So, looking at symbol by symbol suboptimal detection. So, since x n of t is 1 for these values, that means at 2 sampling instance it is non-zero, the samples at the output of the received demodulator filter are y m, which is some b m plus noise, and b m is ith amplitude plus the I minus 1th symbol. So, these are the transmitted sequences. So, because of intersymbol interference, we are seeing controlled intersymbol interference because of the symbol and the previous symbol which we had drawn in the picture here. So, there is and interference here, right. So, that is what we had depicted, and this is the noise, of course, we have stated. So, when we start building the receiver, we will take a look at the noise free received samples, so as to construct the receiver algorithm, and whatever noise is present would cause impairments in the performance. So, going ahead, so ignoring noise and considering I m to be plus minus 1. So, we are limiting ourselves to the situation where it takes binary values, and we also say that let it take these values with equal probability. If the probability changes, our calculations would be different, and generally equal probability is valid. Our b m over here can take minus 2 or plus 2 when both of them are minus 1 or both of them are plus 1 simultaneously. So, if each has a probability of half, probability of getting 1 and 1 is half multiplied by half, that is 1/4, and probability of getting minus 1 and minus 1 is similarly probability of getting minus 1/2 multiplied by that of half. So, we are taking the joint and considering these to be independent sequences is 1/2, and 50% probability of other situations, that is 0, that means a plus 1, a minus 1, or a minus 1 and a plus 1. So, there are two conditions, each with 1/4 probability, adding to give half probability, which we get as 0. So, given this, we consider at this point that I m minus 1 is detected symbol from the m minus 1th signaling instance. So, suppose we begin with that I m is detected correctly, and that can help us in the decoding procedure. So, if this confuses, we can begin with the state where there is no transmission, that is 0 amplitude. When detected, the first detected symbol is let us say I 0. So, its effect on B m can be eliminated by subtraction, because you can see B m is given by this. So, if I know I m, I can take away I m minus 1. If I know this, I can take away I m minus 1 and I will be left with I m. So, if I have detected this correctly, I will be left with only the current signal. So, if I can do this, that means if I can eliminate I m minus 1, I can detect I m. Now, because of I m minus 1, error in detection because of noise, because there is noise present, and we have discussed how noise affects the detection, and there is a detection probability and probability of error. Therefore, I m may also be erroneous. So, once I m is erroneous, the next symbol may also be erroneous, and so on and so forth. So, this procedure is known as, or this situation is known as error propagation. So, we would like to see if it is possible to remove this error propagation. So, error propagation can be avoided by precoding techniques. So, if we are using certain precoding techniques, we can remove the error, right. So, what we can do is at the transmitter we can produce P m as d m modulo 2 subtraction of P m minus 1, where P m is the output and d m is the data sequence of zeros and 1. So, P m would be zeros and ones using a memory of the previous output. So, this, since it is modulo 2 operation, we are going to get P m as zeros and ones. This is the incoming bit stream. So, there is some kind of a memory involved. So, there is some process similar to the NRZ I that we had seen before. So, if we set I m equals to minus 1, in that case our P m would be 0, and if we can set I m as 1 if P m is 0. That means, whenever P m is 0, I would send a minus amplitude level, and when P m is 1, I would send a plus amplitude level. So, this could be minus d plus d, or it is represented as minus 1 plus 1. So, this is the amplitudes, pulse amplitude modulated binary pulse amplitude. So, these are the two values in consistent with this description over here. So, based on the bit sequence here, I get these amplitudes. So, hence we could write I m as 2 times P m minus 1, because P m takes a value of 0, I m takes a value of minus 1, which is depicted here, and P m takes a value of 1, I m takes a value of 2 times 1 minus 1, which is 1, which is depicted here. So, the noise free output at the receiver. So, you would recall that the received signal is this. So, noise free means I am looking at removing this only at B m, right. So, that means I am looking at this and not at this. As I said, we want to construct the receiver by focusing on this and not on the noise, and then the noise would affect our decisions, of course. So, B m is equal to I m plus I minus 1, I m minus 1. So, we have all the necessary expressions visible now. B m as this, that is what we have written. I m is equal to 2 P m minus 1. So, we use here 2 P m minus 1, I m minus 1 is 2 times P m minus 1. So, we have this result 2 times P m plus P m minus 1 minus 1. So, what we get is P m plus P m minus 1 is, so we have B m is B m by 2, half of B m plus of 1, that is what we have over here. Now, since we know that by this expression we have d m is equal to, sorry, P m is equal to d m modulo 2 subtraction P m minus 1. Therefore, d m, from this we can say d m is equal to P m modulo 2 addition of P m minus 1. So, proceeding with this, we can write P m plus P m minus 1 that we have over here is B m by 2 plus 1. We use this over here. So, we have d m, another variable which is basically given here, right. The same variable is continued here, is half B m plus 1 with modulo 2 operation, modulo 2 because it is restricted to a value of 0 and 1. So, that would mean that if B m takes a value of plus minus 2, we have seen that B m takes a value of plus minus 2, right. We would choose d m to be 0, and if B m takes a value of 0, we would choose d m to be 1. So, that means we have recovered our data sequence at the receiver by simply comparing B m to a threshold which if it is near 0 we would set it to be 1, if it is closer to plus minus 2 we would set it to be 0. So, in that fashion we can recover the data sequence that has been transmitted by virtue of cancelling the interference right at the transmitter. So, the receive filter will be having y m is equal to b m plus noise. So, we would set that if, because it is 0 and we can say there is a 0, there is a 2, there is a minus 2. So, a decision point would be somewhere in between, which is 1 and minus 1. So, if b m, so if I receive y m which is b m plus noise, that means b m is plus minus 2 or 0 plus noise. So, if it falls within this range, I would declare that data received is 1, that means if this is 0 it is 1. So, going by this, if the received signal with noise is lying within this range plus minus 1, I would decode it as 1, whereas if it lies in this range I would decode it as 0, going by this. Look at this, this connected with this range and which is depicted that y m is greater than 1. So, this is midway between and we get d m. So, this is how we would build our receiver. So, we can extend this technique to M-ary PAM. In case of M-ary PAM, we have the noise free sequence b m as which is as did before, but these are 2 m minus 1 possible values, because now this not only take plus minus 1, but it takes larger values up to 2 m minus 1. So, at the receiver we would still have I m equals to 2 p m minus m minus 1, and this is the precoded sequence going by the previous notations, and p m would be modulo m operation. So, this is the precoded operation as you do at the transmitter, right. So, the noise free output at the receiver in a similar fashion can be taken as I m plus I m minus 1, which is the same expression as we did before, but here there is an m minus 1, previously we had 1. So, there m was 2. So, 2 minus 1 is 1. So, minus 1 is what we had for binary level, and hence p m plus p m minus 1, which is again a similar expression as we did, as we had seen before, and there m was 2 and here m is general, and d m can be p m plus p m minus 1, that is the data sequence is what we have over here, which is half of b m plus m minus 1 in modulo manner. That means, we take b m and we would decide on the value as we did for the binary situation, right. So, that way we can easily extend this to M-ary PAM and get our received signal. So, in case of the modified, that is the red figure that we had shown, that means, if we had modified, this is known as the modified duobinary, right. If we use the modified duobinary, so we have minus 1 at n equals to 1 and 1 at n equals to minus 1. So, at the negative side you had a plus 1, at the positive side you had a minus 1, and your demodulation would be a minus over here instead of plus because of this minus sign, So, we had a plus earlier. So, I m would be the m level sequence. So, in general it looks like p m minus m minus 1, and p m is this one, which was earlier a modulo 2 subtraction, here it is modulo 2 addition, and the detection rule for recovering the data sequence would be, in absence of noise, is of course this. With noise there will be thresholds like we considered here. So, similar to the thresholds that we had considered, we must consider thresholds in this case and would decode the received signal. So, as we stated in the beginning, that all these methods are suboptimal because we are looking at symbol by symbol, and the other way of recovering the signal would be to consider maximum likelihood sequence detection or maximum likelihood sequence estimation, which we had described in an earlier lecture. So, by constructing the chain of received sequences, if we should be able to compare the probability of one sequence with another and another given a particular transmit sequence. That means, we will change the transmit sequences and compare the posterior probabilities whichever transmit sequences maximizes this probability, we are going to select that in case of maximum likelihood sequence detector. So, with this we cover our discussion on techniques by which we can send signals through band limited channels. So, just a quick summary that we could restrict our signals to a bandwidth of 2 W, but in that case we would stretch our symbol duration to be longer than the typical Nyquist, and the excess bandwidth could be used for a smooth roll off. But since we have stretched the bandwidth, it causes intersymbol interference, and this intersymbol interference is introduced consciously. So, it is controlled intersymbol interference which could be addressed at the receiver, and then we saw that one could pre-code at the transmitter and could decode symbol by symbol at the receiver. Just a reminder, we developed the receiver algorithms by considering no noise, and noise would definitely affect the performance. And finally, as a last word, for the best performance one should use the maximum likelihood sequence detector because there is memory in the transmitted signal. With this, we are now geared to move into the channels which are non-ideal. So, let us proceed to the discussion of channels which are non-ideal. So, in case of non-ideal channels, so channel can be characterized as a band limited linear filter which we have already said, with an impulse response h c of t and frequency response h f, which is having a gain and a phase term, and these are related by Fourier transform relationships. If it is the ideal channel, we would say that the gain is constant and there is a linear phase associated with that, and if it is non-ideal, we would have intersymbol interference which we described through the impulse response diagram earlier. So, this intersymbol interference is a major obstacle to achieving higher bit rate, as we have said, because of complexity in calculations. So, to reduce or improve the situation, we can use equalization or signal processing at the receiver. So, by signal processing we mean that we are going to use some form of filtering, because at some point we stated that the complete transfer function of the system, which is the transmit filter, the channel transfer function followed by receive filter as well as equalizer together should give us a 0 ISI situation. Since we said that channel is not known a priori, we would restrict the raised cosine with pulse shape to the transmitter and receiver filters, and we would restrict it to root raised cosine. Then we said that whatever is remaining with the channel could be compensated by the equalizer filter, so that the channel and the equalizer filter could produce an ideal response. So, when we take together the whole set, we would produce a 0 ISI received signal sequence. So, if we look into the study of equalization techniques, there are several equalization techniques which are known. One is the maximum likelihood sequence estimator. We have seen the general structure of it, that is extended to apply in equalization. In the filtering techniques, we can classify it as linear, which could be zero forcing or MMSE. We will see them. It could be non-linear, that means decision feedback equalizer or turbo equalizers, which we will not see. It could be categorized as preset, that means fixed, or adaptive. We will partially see some form of adaptive equalization, and it could be symbol spaced or fractionally spaced. Further, you could also use precoding techniques. One famous precoding technique is the Tomlinson-Harashima precoding. We have already seen one precoding technique in the earlier discussion. So, here we have the overall system transfer function, which includes the transmitter filter, channel, receiver, equalizer. So, these two we have already assigned, let us say root raised cosine. Of course, we should remember that the receiver knows the kind of signaling that transmitter is going to use. This is part of a protocol. So, only a transmitter and receiver pair which has been designed together following a particular technology or standard are able to decode each other. So, suppose I use a full response signaling at the transmitter and I use the filter for partial response signaling, things are going to go hayway. So, we must use the corresponding pair of transmitter receiver filters at the both transmitter and receiver respectively. So, now we focus on the channel and equalizer. This we have already seen our root raised cosine which produces a raised cosine. Now, whatever should be the channel, the equalizer should be able to cancel the effect of the channel, and that is why the name equalizes the channel effects. So, in practical systems, as we said, channel is not known a priori and these have been converted to root raised cosine, so that overall it is raised cosine, and as we just mentioned that HEQ has to compensate for the channel. So, now a quick description of things is that, as we said, that let us take a look at the channel impulse response which we had seen before. All right. Suppose the channel has an impulse response which is like this, and then there is another echo and continuous signals are sent. So, there is ISI. So, we want to pass this through a filter so that we get a raised cosine. Overall, we have seen that these two combine to produce the raised cosine. So, that means these two together remaining should produce an ideal filter. In other words, in the frequency domain, their response should be flat in terms of gain and there should be some linear phase. So, whatever is the channel transfer function, it should equalize the channel transfer function to produce. So, if this is the impulse response, the channel transfer function could be something like this. So, if we have to produce a channel transfer function which is in this manner, we should have a sync response composite. If we think of infinite bandwidth situation, in that case this should be converted back to an impulse. If the response is converted back to an impulse, we will get consecutive trains which are impulses and there would be no intersymbol interference. So, this leads us to having the equalizing filter made equal to 1 upon the channel transfer function. That means, when these two are multiplied, it produces a 1, leaving these two products to give a raised cosine. That means, the gain is inverse of the gain of the channel transfer function and the phase is the conjugate of the phase of the channel transfer function. So, together if it produces a 1 as the frequency response, it produces a value of 1. If you take the inverse Fourier transform, it should produce an impulse in the time domain. So, that means, if the channel produced an impulse response in this fashion, when it passes through an equalizer filter, it should produce an impulse at the sampling instants and 0 at all other sampling instants. So, that means, it is not allowing any ISI or it is forcing the interference to 0. So, these kind of filters, as described by the expression here, are also known as zero forcing equalizers, because they force the impulse response after passing through the equalizer filter, composite impulse response, to be then impulse. An impulse means it is unity at the first sampling instant and it is 0 at all other sampling instants. So, which means that if you have an impulse and zeros elsewhere, if I send another signal, there will be no interference, there is no interference. So, it is forcing all interference components to 0, because in the frequency domain you have a composite response which is flat and 1, in the time domain it is an impulse, and therefore, this kind of an equalizer filter is known as a zero forcing equalizer. In the next lecture, we will see some other kinds of equalizers, and thereafter we will proceed to design of other important algorithms of the communication system, such as synchronization. Thank you.